Afternoon, folks. Hope everybody is holding up well wherever you are. I'm here today to tell you about some science in the 18th century. Now, we have already begun discussing the Enlightenment. The last lesson or two that I posted here have dealt with the core concepts of Enlightenment science. And we've already begun dealing a little bit with science in the 18th century, since the Newtonian Revolution begins in the 1600s and continues into the 1700s. I want you to keep in mind as we continue through here that the basic principles of Enlightenment science are going to be persistent throughout this time. We're still going to be looking at a worldview dominated by an increasing growth in reason, in secularization, in the faith in rational rather than supernatural explanations, and a growing idea in the equality of humans and the ability of everyone to participate equally in society. That's kind of the intellectual backdrop of the entire Enlightenment, and it's informing some of the science that goes on. Now, hopefully you've already listened to my lesson on the Newtonian Revolution, which in a lot of ways is going to define everything else that happens in science for the next century or so. In part, this is because Newton has given us, or Newton and his contemporaries, have given us this notion of an empirical way of looking at nature, that we are really internalizing this core idea that the only valid way to consider nature, the only really solid way to model natural phenomenon, is to do so with consistent mathematical rules. That mathematization of our study of science is going to be tremendously helpful, particularly to the growing fields of physics and chemistry. And we're going to find that Newton's laws serve as a really important jumping off point for the development of those fields. It is not a coincidence that chemistry makes the final transition away from alchemy during the 18th century. A bit ironic that Newton himself was an alchemist, one of the last alchemists, when it's in a lot of ways his principles of rational empirical study of nature that are going to sound the death knell for that ancient practice. We're also going to find physics is going to grow considerably during this time. The existence of Newton's laws gives us a way of testing for the existence of new natural forces. We know that anytime we see motion at work that cannot be attributed to a basic force of gravitation, that other forces must exist in order to provide that. The Newtonian Revolution is therefore going to give physics new tools for investigating how other forces of nature might work. A lot of the story of science in the 18th century is therefore going to be the story of the growth of the physical sciences, the growth of chemistry and physics in particular, as we lay down some really concrete principles for getting them rolling. Now, some of this is going to be mathematical in nature. Some of this is going to be based on a couple of really crucial discoveries. We're going to find that during the 18th century, a couple of major specific discoveries are going to really advance those fields. In the realm of chemistry, we're going to have a lot of work done with the science of gases. There is an entire little sub-discipline of early chemists that we sometimes call pneumatic scientists, P-N-E-U-M-A-T-I-C. Your pneumatic scientists, as they're known, are going to be the folks who are experimenting with gases. Starting with the work of Robert Boyle, there's a lot of research being done with the nature of gas, how it behaves, and a growing awareness among scientists that gas is not all one thing, that air is not one singular substance, that in point of fact, there's more than one kind of air. So we're going to see a lot of these pneumatic scientists during the 18th century identifying specific airs, as they call them, specific kinds of air, culminating in the discovery of oxygen, which is going to be a major step forward for understanding how a lot of chemistry works and for overturning the phlogiston theory that has persisted since the Age of Reason. Now, pardon me, I just realized a thing I should point out here as a little side note. If you are one of my students taking this History of Science class, you'll find a handout about all of this on our Blackboard site. You might want to refer to that for spellings of terms and people's names as this is going on. Also, good time to mention, if you are one of my students, I'm not going to be talking about specific assignments in this video. I'm strictly giving content here. Assignments will be posted to Blackboard later. Now, the other really big discovery that's going to move both physics and chemistry forward during the 19th century is going to be the discovery of this thing we call electricity. That electricity has been known about in some form since ancient times, going all the way back to the time of Lucretius. We had awareness of static electricity as a phenomenon. The Greeks were aware that if you took a piece of amber and rubbed it with a bit of silk, that it would gain a static field, which would attract feathers, bits of dust, and other very light particles. In fact, the word electricity is derived from the Greek word elektron, meaning amber. Well, we're going to find that electrical science is going to leap forward by a tremendous amount during this time. That we're going to have lots and lots of advances in electrical science. Like I said, Newton's laws give us a toolkit for realizing, hey, there are forces of nature out there other than gravitation that can work in different ways. And electricity is one that's going to get a lot of attention in the 18th century. In fact, I think a good point to start off, a good figure for bridging the gap between the Newtonian revolution and the rest of the science of the later Enlightenment, is going to be a fellow who does not get a lot of press in the history of science, an Englishman by the name of Stephen Gray. Stephen with a PH. Gray was born in 1666, died in 1736. And he acts as a kind of a good figure for doing all of this because in some ways he is the last real victim of Isaac Newton's somewhat spiteful approach to how he dealt with his rivals. Now, Gray was an amateur scientist, a gentleman scholar, began his career as a relatively humble man. He was a cloth dyer, never wealthy, completely self-educated in science. He became interested in astronomy and began grinding his own lenses at home to build his own telescopes. Gray started doing his own personal astronomical observations, made a few minor discoveries, and wrote about his findings to John Flamsteed. Remember him, the Astronomer Royal of England. Flamsteed was impressed by Gray's work, and about the time that he's starting to communicate with Gray is about the time he's becoming estranged from his assistant, Edmund Halley. So, when Halley leaves Flamsteed's service, Flamsteed invites Gray to join him at the Royal Greenwich Observatory as his new assistant, and Gray takes that position. Now, I should point out right now, Stephen Gray is not doing any personal research on the same topics as Isaac Newton. He is not interfering with Isaac Newton in any way. But, that said, because he is attached to John Flamsteed, Newton is going to go out of his way to wreck Gray's scientific career. No other reason. Time and again, Newton is going to shut down Gray's opportunities to join the Royal Society of London. He's going to block him from getting academic postings and limit the circulation of his research as much as he can. In a time period when peer review by an organization like the Royal Society of London is increasingly vital to being taken seriously as a scientist, at a time when that kind of scientific networking is increasingly important, this is effectively stymieing Gray in his scientific career. When Flamsteed dies, needless to say, Edmund Halley is not going to keep Gray around as a new assistant, and he finds himself kicked out of the Greenwich Observatory. Before his death, Flamsteed, who sees the way that this is going, manages to leverage his connections with the crown to secure a pension for Gray. And Gray spends the last years of his life living at the Charterhouse. It's a poor house in London, basically intended for gentlemen of distinction who have fallen on hard times. And Gray lives out his days on a meager government pension there. Now, cut off from the observatory and with few resources of his own, Gray is not able to effectively do astronomy work, which increasingly needs expensive telescopic equipment. But he doesn't lose his interest in science, and he turns his attention to another field, the little explored study of electricity. Gray is able to cobble together simple materials at the Charterhouse to do the kind of experiments that he wants to do. He hand designs a simple machine, a pedal-driven device that rubs a ball of sulfur in order to generate a static field. Later, he improves on this by using a glass rod, which generates more efficient static. In this way, Gray is able to create consistent static electrical fields for his research and makes a number of very important discoveries in the budding science of electricity. There we go. My head was slipping below the horizon there. Among other things, Stephen Gray's experiments allow him to discover that electricity seems to behave in two distinct ways. He is aware that there are electrical fields that will flow towards some objects and away from other ones. He discovers that he can transmit electrical currents that along an object, a conducting object, for considerable distances, that he can basically send a current along a conductor for as far as he wants. He learns that certain materials are better conductors than others, discovers the concept of conductor and insulator in electrical science. He realizes, however, that any object can be made to hold an electrical charge, which he calls electric virtue. That's the term that he uses in the course of his work. He discovers that there seem to be... Sorry, brain just shut down for a second. He discovers that this is a really important thing about electricity, that it's a more powerful force than gravitation. He does this with a famous exercise called the flying boy experiment. And what he does is he gets a street urchin from London, gets the boy to come into his laboratory, totally not dodgy, getting a little boy to come into your basement to do experiments with you, and he suspends him from the ceiling of the cellar on silk threads. Then he attaches a wire to the boy and runs an electrical current into his body. Now, because the boy is not touching the ground or anything, his body holds the charge. He's not shocked or anything by this. And Gray discovers that the boy can attract tiny bits of paper and feathers to his hands with the electrical field that he's holding, thus showing that the force of electricity is more potent than the force of gravitation, and is able to lift objects in opposition to gravity. Gray's discovery that current is seemingly attracted by some objects and repelled by others leads other electrical scientists with whom he is corresponding to build on that. A French scientist by the name of Charles Dufay, D-U, separate word, F-A-Y, and you don't capitalize the do. Charles Dufay, born in 1698, dies in 1739, makes the discovery in 1733 that there seem to be two kinds of electrical fluid, as he calls them, that electricity seems to exist in two distinct forms, which Dufay names vitreous and resinous electrical fluids. Today we know them better as positive and negative currents. Now, Stephen Gray receives some belated recognition for his achievements in electrical science. After Isaac Newton's death in 1725, Gray is finally admitted to the Royal Society of London in 1632. Of course, he's in his twilight years at this point, doesn't do a whole lot more useful science after that, and dies in 1736, buried in a common pauper's grave with no distinct marker. Sadly, his research largely goes ignored. Most of the key things that Gray discovered get independently rediscovered by other people who end up getting credit for them. And to this day, there is no scientific monument or memorial anywhere, to my knowledge, that is honoring the achievements of Stephen Gray. And I think it's kind of a crying shame. So I wanted to make sure that he kind of got his due here, is in many ways the father of modern electrical research, even though his work was for the most part recapitulated by other people. Now, one of those other people who is very, very famous for electrical research is an American. And let's talk for a moment about where science is being done. Now, the focus of this class has admittedly been Eurocentric. There are a couple of reasons for that, in large part because the accomplishments of European scholars from about the Renaissance onward largely formed the modern global scientific paradigm, and largely because, quite frankly, European scholars were not interested in, or even in many cases aware of, the scientific achievements of non-Europeans. So Consequence of that is that although there was indeed scientific work being done in Asia and Africa and even in some parts of the Americas prior to and during the Renaissance, for the most part, that work never made it into the mainstream of scientific research. And so a lot of work was unfortunately lost that way. A lot of good science ended up not becoming a part of the overall development that we're talking about here. Indeed, when the Spaniards conquered Mesoamerica, they stumbled upon an Aztec culture that had fairly advanced astronomy, fairly advanced mathematics, and a decent knowledge of biology. A few intrepid Spanish missionary priests did record some of the Aztec medicinal texts that contained their knowledge of native plants and herbs, but by and large, Aztec scientific and mathematical knowledge was literally burned, that the manuscripts written by Aztec scholars were destroyed by the Spanish because of their supposed pagan contents. So we literally destroyed a lot of good American science as soon as we found it. But let's talk a little bit about science in the American colonies, because that's going to become a thing that becomes important starting in the late Enlightenment. Now, Europeans have been colonizing the Americas since the 1500s. That is well established. The English have colonies in what is now the United States by the early 1600s. But for the most part, colonial settlements in the Americas are not really intellectual centers. The simple fact of the matter is that Europeans tend to view the American colonies as two things. One, a place to dump surplus population, in particular people belonging to unpopular religious movements like the Pilgrims, and two, as a way of extracting resources that will then be sent back to the homeland to produce manufactured goods, a system called mercantilism. And you'll find that the basic way that it works is the colonies send resources back home to England and France and other European countries. Those resources are then converted into finished goods. The finished goods are then sold not only in Europe, but back to people in the colonies. So really, the colonies become both a market and a resource extraction center. But they're not really seen as political entities in their own right. They're outposts. And that sense of otherment and that sense of inferiority, really, is going to be a major factor in motivating the American Revolution. The American Revolution was not just about opposition to taxes. It was also very much about opposition to being treated as second-class citizens by the big governments back home in Europe. So initially, at least, the American colonies are pretty much a frontier. Settlers coming, trying to eke out a living in this faraway land. But once they've been there for a little while and it's no longer just hardscrabble pilgrims desperately trying to get through each winter, you're eventually going to have the growth of towns and big cities. You're going to have urban centers. The New World becomes a functional society, not just a frontier town or two, but a place that has thriving metropolitan areas. Now, you can't have the kind of intellectual engagement in the New World that you have in the Old World when the overwhelming majority of important scholarship is still being done in the Old World. And given that the new discoveries can only make it across the Atlantic at the speed of ship travel, and let's be honest, most ships coming across the Atlantic are not highly prioritizing the delivery of scientific equipment or texts on new discoveries, this means that American scholarship, for the most part, is going to lag behind European scholarship in almost all important respects. But you are going to have American scholars who go back to Europe to be educated and bring home knowledge of the things that are going on there, including knowledge of this thing called science. And you might note I'm using the term science now as opposed to natural philosophy. By the time of Isaac Newton's death, the Latin term scientia, or knowledge, is replacing the term natural philosophy, as it becomes increasingly clear that this thing we call science now is a distinct discipline apart from the other concerns of philosophy. Now, still don't find a lot of infrastructure for this in the New World. By the late 1600s, the Americas do have their own educational infrastructure. When you've got big societies, when you've got cities with lots and lots of people in them, You need people who are educated. You need folks who know how to read and write and keep records. You need people who can do math. You need people who can interpret literature and interpret law. So by the early 1700s, the New World has about a dozen colleges and universities of its own, including many of the famous Ivy League institutions that are still here today: Harvard, Yale, Princeton, Dartmouth, and so forth, the College of William and Mary in Williamsburg, and a few others, mostly along the northern part of the Atlantic coast. Now, for the most part, these universities are providing the basic education that is expected of any upper-class individual. They're providing education for lawyers, for ministers, for basically anybody of wealth and means who is expected to have some kind of education. And while that means courses in mathematics and possibly here and there a course in natural philosophy are going to be part of the curriculum, for the most part, these academic institutions are serving the needs of isolated colonies for having educated professionals for important areas of inquiry. Scholarship as a whole is not really a high priority beyond the practical needs that it serves. And therefore, you're not really going to find a whole lot of natural philosophers in the early colonies. But this doesn't mean no one is interested. By the 1700s, as science becomes more and more established a concept, you are inevitably going to get some American scholars who want to do it, particularly those who have spent some time in Europe and are aware of the intellectual developments there. And the early Americas are going to produce some important scientific thinkers. You might know a few of the names. One prominent figure is a fellow by the name of Dr. Benjamin Rush. Rush is a native of our own Pennsylvania here. Pardon me. Rush was born in 1745, died in 1813. He's the signatory of the Declaration of Independence, served at the Continental Congress for Pennsylvania. During the Revolutionary War, he serves as a physician treating various soldiers' ailments. And following the war and the establishment of the first American government, Rush is appointed the first Surgeon General of the United States. Now, Rush is an interesting figure because not only is he a physician, but he's a scientific physician. He's thinking empirically. He's trying to figure out better ways of doing medicine with the toolkit of science. He gained some fame for his work during a yellow fever epidemic that breaks out in the late 1700s and is the first major crisis faced by the budding American Republic. Rush advocates for hygienic treatments and for trying to keep clean as a way of preventing the spread of infection. Lessons that are obviously still pretty germane right now. In addition, Rush is a research physician with an interest in what today we would think of as psychology and psychiatry. He is going to write one of the first psychiatric texts in which he argues that mental disorders are things that can be medically treated. And he also is the first to argue that addiction is a disease rather than a simple failure of moral character. A fellow by the name of David Rittenhouse, Rittenhouse, is also going to gain some fame as a scientific thinker during the Revolution. Rittenhouse, who was born in 1732 and died in 1796, is a mathematician with interest in astronomy. He's going to help design defenses for the city of Philadelphia, and he's also going to provide astronomical equipment for navigation for the early Continental Navy, and therefore helps with a little bit of military infrastructure technology in that way. And of course, I'm sure all of you are aware of a fellow by the name of Thomas Jefferson. Thomas Jefferson is a polymath scholar with a tremendous range of achievements. You all know at least a little bit about Mr. Jefferson. He, of course, is going to be a significant figure in the American Revolution, author of the Declaration of Independence, big contributor to the Constitution, serves as American minister to France, an ambassador to France in the early days. He's the first Secretary of State, Vice President under John Adams, and ultimately becomes the third President of the United States. But if you asked Mr. Jefferson his biggest achievements, he would say his chief interests were in scholarship and learning. He cited, actually, if you go to Monticello, Thomas Jefferson's home in Virginia, It's well worth a visit. You'll see there a number of simple inventions and contraptions that Jefferson designed to make life easier around the place. He was a tinkerer and an inventor who was always putting together little contrivances to help out with day-to-day life. He was an avid gardener and actually bred several new varieties of fruits and vegetables. He actually introduced the tomato to American cuisine after becoming acquainted with it during his time in Italy. He was interested in applying engineering principles to improve day-to-day life. Jefferson, among other things, invented the lap desk and the swivel chair. And in the realm of pure science, he's also one of the first archaeologists. Jefferson actually conducted archaeological excavations of Native American burial mounds that he found on the grounds of Monticello. And he also curated a sizable collection of Ice Age fossils, some of which that he collected himself, some of which were given to him, and that are still on display at his home. In fact, you all know the Lewis and Clark expedition, the famous expedition sent out by President Jefferson to explore the Western territories, and that was as much about mapping as it was about science. Jefferson actually insisted that Lewis and Clark keep detailed records of the plants, animals, and geological features in the landscape they were encountering and send them back for his study. So Jefferson was a man of science as well as a man of politics. He actually personally considered his greatest achievements to be in the theater of education. If you read his tombstone, the inscription of his achievements on his tombstone includes that he was the author of the Declaration of Independence, the author of the Statute of the State of Virginia for Religious Freedom, and the founder of the University of Virginia. It does not list being President of the United States among his achievements, because he didn't see that as being a truly important job as compared to the other stuff he was doing. By the way, thinking in terms of Enlightenment thought, fun little story about Thomas Jefferson. Some of you might be aware of a thing called the Jefferson Bible. Thomas Jefferson was a big believer in Christian ethics, but he was a deist and did not really find a lot of use for the supernatural parts of the Bible. To him, Scripture was a great source of moral wisdom. It was just a crappy source of supernatural belief. So Thomas Jefferson literally got himself a razor blade, cut out the portions of his Bible that contained stories about the supernatural, and stitched the rest of it together into a collection of moral teachings divorced of divine miracles, which is now called the Jefferson Bible. He had it published in that format, and it's still available today if you want to get yourself a copy, just to exemplify this kind of fusion of religious and scientific thinking that we get in this time. People like Jefferson who don't have a belief in supernatural forces, but are still trying to maintain a religious life even as they're doing scientific work. But, you know, folks like this are the exception rather than the rule. There is not a lot of American science yet, and there's not going to be for a while. But starting in the late 1700s, people like Rush and Jefferson and Rittenhouse are going to be forming the beginnings of an American scientific infrastructure. America is really going to leap forward in its scientific progress in the 1900s. Honestly, it's not going to be until the early 1900s that the United States begins to become a significant contributor to scientific knowledge. But get started here. But, you know, we'd be remiss if we talked about science in the 18th century in general, and American science in particular, without naming arguably the first prominent American scientist. A fellow you all know of, a polymath scholar of very diverse achievements, one Dr. Benjamin Franklin. Franklin was born in 1706, died in 1790. Although we here in Pennsylvania like to claim him because he did spend most of his life here, he was not, in fact, a Pennsylvania native. Ben Franklin was a native of Boston. He was born the 17th child of a poor candle maker. And needless to say, that does not give him a lot of prospects going forward. Of course, Franklin ends up having a very prominent and successful life as a publisher, as a statesman, as a diplomat, as an author, and of course, as an inventor and scientist. Now, as a young man, Franklin has no formal education after the age of 10. He is a voracious reader, however, and largely self-educates. One of his older brothers is a printer, and Franklin is apprenticed to work with him in his printing shop, producing an early Boston newspaper when he's a teenager. During his time as a printer's apprentice, Franklin not only reads quite a lot that's coming into the shop, but he starts getting interested in politics, and he starts writing secret anonymous letters to his brother's own newspaper under the pseudonym of Silence Dogood, who was supposedly an elderly Boston widow who had lots of things to say about the state of politics and the economy in her time period. In those days, it was considered gauche for a printer to put their own opinions in their own newspaper. There was nothing like an opinions or editorial section yet. So the Silence Dogood letters became a prominent feature of the newspaper, quite popular in Boston. Whenever it came out that Franklin was secretly the author of those letters, his brother was infuriated, and Ben fled. He hopped on a ship and sailed off to Philadelphia, and from there went to England. I should point out at this point in time, he was a fugitive. Under law, apprenticeship was a legal contract. He was indentured to serve his brother until the term of his apprenticeship was up, and he ran out on that, which meant he was technically fleeing from the law at that point. So Franklin goes to London, stays there for a couple of years. He actually takes rooms with an English physician by the name of William Hewson, Hewson. Hewson is considered one of the fathers of the science of hematology, the study of the blood. While he's in London, Franklin is going to become acquainted with natural philosophy from a lot of the work being done by prominent scholars there. He actually joins a small scientific society called the Lunar Society, affectionately referred to by its membership as the Lunatics, because they meet on the night of the full moon every month. And there, Franklin gets to know several other prominent scientists of the day, including some folks we're going to talk about later on in this course, such as Joseph Black and Erasmus Darwin, the grandfather of Charles Darwin. So when Franklin finally decides to return home to America, about 5 years later, he's absorbed this growing knowledge of and interest in science and natural philosophy. He goes to Philadelphia, settles down, spends most of the rest of his life there, sets up his own successful print shop in Philadelphia and his own successful newspaper. Has no hesitation to put his own opinions in the news page, kind of the father of the modern editorial. He starts the first American post office, he starts the first American fire company, and the first public library. He also becomes an outspoken advocate, as I'm sure you were aware, for political independence for the colonies. Franklin's essays to this effect actually are a big factor in fomenting pro-independence sentiments. And it's no surprise that Franklin becomes a key architect both of the Declaration of Independence and later of the Constitution, and then serves as America's Secretary of State for a while and an ambassador to France and England, as well as the first Postmaster General. But as political career aside, we're interested in Franklin the scientist. Like Thomas Jefferson, Franklin is a gifted inventor, and he's continuously working on ways to improve life with the knowledge of science. He grinds his own lenses, and as a way of helping correct his own poor vision, he invents the first bifocals. So if you have bifocals, thank Benjamin Franklin. He was the first person to develop that kind of lens. He invented the pot-bellied stove as a more efficient way of heating a home, safer than what was often done with stoves of the day. He invents a glass harmonica. He makes an interesting medical contribution that he's often not remembered for. Benjamin Franklin invents the urinary catheter. He suggests ways of improving the hulls of ships to make them more waterproof. He invents an improved form of the printing press, improvements on anchors and sails. And while he is crossing the Atlantic, which he does a few times during his life, he charts the Gulf Stream, a major warm water current that flows across the Atlantic from the Gulf of Mexico to around England. Discovering the Gulf Stream rapidly speeds up the movement of ships across the Atlantic by taking advantage of that current, and therefore is a great boon to cross-Atlantic commerce. Franklin becomes interested also in atmospheric phenomena, and in particular in the phenomenon of lightning. Now, while he's crossing the Atlantic, he gets interested in the behavior of atmospheric movements. He's the first person to realize that there are multiple layers to the atmosphere, that the movement of clouds far overhead is not always following the same direction as the prevailing wind at ground level. but in particular, lightning draws his attention. There's a wonderful biography of Franklin about his electrical research called Draw the Lightning Down, well worth checking out. But Franklin decides to do a series of experiments in this regard. He wants to learn more about what this electrical force is. He is aware of the works of Charles Dufay, Stephen Gray, and of another French electrical scientist by the name of Charles Augustin de Coulomb. That's D-E, separate word, capital C-O-U-L-O-M-B, Coulomb, de Coulomb. You might know Coulomb's law, which is the inverse square law of electrical force. But Franklin is aware of this electrical work that's going on and sets out to do some of his own. Specifically, he wants to demonstrate that lightning is an electrical phenomenon. Keep in mind that since ancient times, we've had this idea that lightning is fire in the sky. Not surprising, considering zaps down to earth, right? It hits things, starts fires. People would think it was fire. But Franklin notes the static fields that form around objects in the lead up to thunderstorms and begins to wonder if, in fact, lightning is electrical in nature. He begins doing crude experiments. Now, it's already known at this point in time that you can trap electricity in a simple kind of battery called a Leyden jar, capital L-E-Y-D-E-N. A Leyden jar is basically a glass jar with a metal rod in it that you can run a current to and temporarily store electrical potentials. And Franklin uses Leyden jars to do a number of experiments. But he wants to see if he can literally catch lightning in a bottle. So Franklin does a series of experiments to work on this, to demonstrate that lightning is electrical. He proposes an experiment in which he suggests that what you could do is attach a metal key to a kite, fly it during a thunderstorm, and that if lightning is in fact electrical, since it has been well demonstrated by now by Gray and others that metal is conductive, that it will attract the lightning, and that the current will then flow down the string of the kite and potentially be trappable in a Leyden jar. Franklin's famous kite experiments, I should point out there is some dispute over whether he ever actually did it. We know the Franklin experiment was first done not by Benjamin Franklin, but by a French scientist he was in correspondence with, a fellow by the name of Francois Dalibard, D-A-L-I-B-A-R-D. Dalibard was born in 1709, died in 1799, and he carried out the Franklin experiment, first known time it was done, on May 10th of 1752. He did not, however, use a kite. Dalibard used a 40-foot iron rod driven into the ground to collect his currents. It is believed, based on some of his surviving notes, that Franklin himself may have performed his own experiments later that year on... eye-watering here. No, you're not supposed to touch your face right now, but I've been inside for a week and a half, so I think it's probably okay. Franklin himself is believed to have done that experiment a little bit later on that year in June or July. Several other people, I should point out, also did attempt the Franklin experiment, having heard about the results here, and several of them died doing so. More than a half dozen electrical scientists in Europe died attempting to replicate the experiments. And they did this basically by ignoring some of Franklin's setup advice and not properly grounding themselves beforehand, which meant that they got zapped by the current coming from the lightning bolt. Now, the Franklin experiment very clearly demonstrates that lightning is an electrical phenomenon, and it leads Franklin to the invention of the lightning rod as a method of protecting tall buildings from lightning strikes. Very important safety tool. But it also gives him a reliable way of capturing lots and lots of electricity. Franklin is able to do that, catch lightning in Leyden jars, and then use the stored current to do a wide variety of experiments. He famously goes on a quote-unquote electrical picnic, as he calls it, to demonstrate the practical value of electricity, in which, using stored currents, he electrocutes and cooks a turkey. By the way, Franklin believed the turkey should be the national bird. He thought it was a purely American animal, unlike the eagle, and also thought the turkey was much more intelligent than the eagle. But so he did this by way of demonstrating the practical possibility of using electricity for applied purposes. And he suggests the idea of an electrically powered range, which will be built much later by other people. Franklin also demonstrates using his electrical experiments that what had previously been called vitreous and resinous electrical fluids were in fact basically two elements of the same force, that he realized what he was seeing was the movement of current from one object to another. And he renames this positive and negative electrical charge, and conceives the law of conservation of charge on the basis of his research. Although I should point out that as compared to our modern understanding of electrical charge, he reverses the things we call positive and negative. What today we understand as positive charge, the movement of current away from an object, Franklin calls negative, and what we understand today as a negative charge from receiving the flow of electrons, Franklin called positive. So the terminology has been flipped since his time, but he was aware of the basic concepts involved here. He also, and this doesn't get a lot of press, tries to apply electricity for medical applications. Specifically, he invents a thing that today we call electroshock therapy, in an effort to use electrical currents to treat people who are suffering from epileptic seizures and to treat people who have had strokes in an effort to improve their symptoms. Although he's not very successful at this, he does establish the idea of using electricity to treat brain disorders, which remains in use, actually even in limited form to this day, for treating certain forms of mental disorders. Now, Franklin's work with electricity gets a lot of press, kind of puts him on the map as a scientific thinker. And in 1743, he is going to found the American Philosophical Society in Philadelphia, the first distinctly American scientific society. His electricity research also gets him some attention in Europe. Franklin is going to become the first American member of the Royal Society of London in 1756. Prior to this, he also receives honorary doctorate degrees from Harvard and Yale universities, and from that point onward is commonly called Dr. Franklin. I should point out, here's a little fun tidbit for you, that if you only have an honorary doctorate as opposed to an earned doctorate, you are not supposed to call yourself doctor. That is considered bad form. You're allowed to put, PhD, HC, honorarium causus after your name, but you're not allowed to actually go by doctor. Benjamin Franklin is allowed to go by doctor. That is a specific exception that is written into the rules of academic protocol, that Benjamin Franklin, with his honorary doctorates, is allowed to call himself Dr. Franklin. Now, Franklin is going to spend much of the rest of his life involved in public service. He continues to do his little scientific experiments on the side here and there. Towards the end of his life, he suggests the possibility of refrigeration technology, demonstrates that he can use a flask of ether and a bellows to cool off a quantity of mercury. He never actually invents a practical refrigerator, though. And he also gets involved in the question of the resurrection of life, the idea that perhaps electricity or other forces could bring people back to life, that science one day might be able to raise the dead. And actually, I quote from his journals, in which he says here that perhaps the body could be preserved for later resurrection. And he says, quote, "I should prefer to an ordinary death, being immersed with a few friends in a cask of Madeira, until that time there to be recalled by the solar warmth of my dear country. But in all probability, we live in a century too little advanced and too near the infancy of science to see such an art brought in our time to its perfection." Franklin is, of course, not preserved in a cask of Madeira. He dies in Philadelphia in 1790, is buried there, and remains dead to this day. Now, two little postscripts to the life of Benjamin Franklin. One, he has left a tremendous legacy, a political legacy, a scientific legacy, an intellectual legacy. He's also left a tremendous personal legacy, in the sense that it is not all that big of a claim to be able to say that you are descended from Benjamin Franklin, inasmuch as a few months before his death, Benjamin Franklin became a father for the 103rd time. He had a very large number of illegitimate children, plus a few legitimate children, including a number of illegitimate children from his times in England and France as a political figure. He was viewed as kind of a celebrity when he traveled to England and France after the Revolution. Dr. Franklin, the great writer, the great scientific thinker, the great political theorist, and apparently, despite being a kind of portly, bald guy, it got him some attention. But the other interesting legacy that Franklin leaves, if you go to London today, you can visit the Franklin House. It's preserved there. It's the house that he and William Hewson lived in back when he was in London in the 1700s. Now, the Franklin House was being renovated in 1998. They were doing some restoration work, and they made a ghastly discovery. Namely, tucked under the floorboards of the Franklin House were 6 skeletons of children and 4 skeletons of adults, dating to approximately the mid-1700s. Now, if you take a look at these skeletons, you're going to find that they have neat surgical cuts on many of the bones. Skulls carefully cut off, arms sawed through neatly at the joints. So what the heck is going on here? In order to answer that question, let me tell you a little bit of a story about medical dissection. Now, since the time of Vesalius, you already know that medical dissection has become a key part of how we learn medicine. You can't really be a physician without learning to dissect a body by the 1700s. That's how you learn your anatomy. Well, there ends up being a conservative backlash against medical dissection in the mid-1700s in London. Well, not just in London, but in England as a whole. The Church of England begins speaking out against it, saying that this is an abomination against the way of God and man, that you should not be poking around in God's finest handiwork, that the things of the body of human life were not meant for man to know. And England ends up banning cadaver dissection. Now, this does not eliminate the need for physicians to learn anatomy. It's become a vital part of what they do by this time. But what it does lead to is a lot of surreptitious grave robbery, as desperate medical students and physicians begin turning to the only source they can to get bodies. A curious profession develops during the 1700s, known as the resurrection man. The resurrection men are paid grave robbers, basically people who will go into cemeteries, dig up freshly buried bodies, and sell them to physicians. And then those physicians will conduct secret autopsies and dissections, oftentimes in university basements for the benefit of their students, and sometimes in their private homes. Recall that Franklin was living with William Hewson, a significant physician and medical researcher, and he had a number of students who studied under him. In all probability, those skeletons tucked under the floorboards were people who had been autopsied by Hewson. Bodies probably acquired from a resurrection man that Hewson and his students were examining as part of their critical learning. And although this is only tangential to Franklin's life, it is difficult to imagine that a man of his scientific interests was living in this house with a physician who was doing secret dissections and that he wasn't involved somehow. So in all probability, Benjamin Franklin was involved in some secret anatomical dissections during his brief time in England, which might account for his interests in the medical applications of electricity and in catheterization as kind of an odd little side note in his history of research and invention. Incidentally, the phenomenon of medical grave robbing is going to persist for quite some time. Even after it becomes legal again, there's often a shortage of bodies, and therefore grave robbery for medical schools becomes a long-standing and gruesome tradition that lasts well into the early 1900s. Here in the United States, that was particularly a problem when medical schools began to get established, and a lot of bodies were sold surreptitiously to the budding medical schools. You might be aware of the famous serial killer H.H. Holmes from the book The Devil in the White City. He was a physician in Chicago who, during the late 1800s, lured travelers into his murder castle, his hotel that was actually a series of torture chambers and medical laboratories, killed them in gruesome ways, and then sold their bodies to medical schools on the sly. Holmes was himself a physician, so he had some personal academic interest in this regard, and ironically enough, when he was hanged, he requested that his coffin be immediately entombed in cement to prevent anybody from robbing his grave. Now, to kind of resolve the resurrection man problem in England in a somewhat gruesome way, there ended up being a pair of enterprising grave robbers philosophers by the name of Burke and Hare. Burke and Hare were a pair of Irish resurrection men, ne'er-do-wells, William Burke and William Hare, who worked together in the enterprise of grave robbing between about 1827 and 1828, late 1820s there. And they took a very direct approach to the matter in that they determined that, why wait for somebody to die? Why not just cut out the middleman? And what they began doing is actually cautioning people, killing them, robbing them, and selling their bodies after the fact. They partnered in this enterprise with a Scottish physician by the name of Robert Knox out of the city of Edinburgh, which was at that time the site of the biggest medical school and most successful one in Europe. And Robert Knox would cheerfully buy bodies from Burke and Hare. He would let them know, oh gosh, man, I really wish I had the remains of a middle-aged woman for my lecture tomorrow, or it'd be really helpful to have an elderly man for my anatomy studies. And Burke and Hare would just so happen to find the right body for him. And Dr. Knox would just carefully turn it over so you didn't see the kosh on the back of the head. Now, Burke and Hare eventually did get caught at their crimes. They were going to be caught up hauling a body home one grisly night. Burke was hanged for the crime. Hare turns state's evidence and ratted out Burke, and as a result, got off scot-free. Nobody really knows what happened to him. Robert Knox's career was ruined by the whole stink of the crime, but he himself never faced any charges, and he ended up finishing his days as a practicing physician in London. But their grisly crimes actually led Parliament to take action. In 1833, England finally passed the Anatomy Acts, a series of laws which for the first time created a channel by which you could donate your body to science, and therefore established a method by which universities and medical schools could get legit, non-robbed corpses. Incidentally, there's a grisly little skip rope rhyme, jump rope rhyme that kids sang in the streets of Edinburgh for decades after these crimes that's kind of inspired by Burke and Hare's grisly grave robberies. And the rhyme goes like this: up the close and down the stair, butt and bend with Burke and Hare. Burke's the butcher, Hare's the thief, and Knox is the boy who buys the beef. Kind of like that one. All right, so a little bit of a digression into some anatomy and medicine there, but we can see that we're building some science, we're building some American science, and we're starting to explore this exciting and intriguing topic of electrical force, which is, of course, going to be very important to establishing physics as we know it. Now, like I said, though, electricity is not the only big thing that is being discovered in this time. We are making some important discoveries in other areas as well. We are making some vital contributions to the development of chemistry. Chemistry as a field is really starting to take off. Alchemy is falling away. The old mystical ideas of the philosopher's stone and the elixir of life are really not holding a lot of water anymore. And so an empirical chemistry, inspired by the methodologies and by the principles first laid down by Robert Boyle, his skeptical chemist, are beginning to really get established. So let's talk now about some chemistry. What kind of important work is going to be done in that discipline? All right, so some chemistry. I think a good place to begin taking a look at the chemical sciences here is to start with some of these pneumatic scientists, the folks who are beginning to realize that air is not all one thing. So we were in Scotland a minute ago, University of Edinburgh with some grave robbing. Let's stay in Scotland for a bit and talk about a Scottish chemist and physician by the name of Joseph Black, a name you might know from a chemistry class somewhere along the line. Black was born in 1728, died in 1799, native of England, born in France. His father was there as part of the family's wine trade at the time that he was born. He was educated at the University of Glasgow, got a position as a professor of medicine at Glasgow later, after receiving his medical degree from University of Edinburgh. Now, Black was never married, devoted most of his time in his free time to scientific research when he was not teaching medicine, and his biggest area of interest was what we would call chemistry now. Now, among other things, Black did experiments with gases in sealed compartments, much like Robert Boyle had done, and Black made the discovery that both a candle and a mouse in a sealed container will eventually suffocate. That you put that burning candle in that container, it will run out of oxygen in short order and go out. Put the mouse in there, a little bit longer, but it too will run out of oxygen and, well, short out. And Black came to the conclusion that there was, in fact, a common factor necessary in the air that both the mouse and the candle required. Not the first person to come to this exact conclusion, but he begins experimenting with the contents, and he realizes that that container contains a kind of air that is different than the mixture of air around us. That there's a kind of air in there which cannot sustain a fire or a living organism. And he names that substance fixed air. We're going to find a lot of these kind of fanciful names for gases early on. Fixed air is what he calls what today we know as carbon dioxide. Further experimentation reveals that not all organisms work the same way. That whenever he puts a plant in the sealed container with the mouse, both of them can sustain indefinitely, as long as the mouse is fed. Black concludes that fixed air is therefore a necessary component of the respiratory processes of a plant, which is the beginning of exploration of what we call photosynthesis now. Black also does some other miscellaneous work in the chemical sciences. He invents the analytical balance as a tool for precise measurements in chemistry, a very important step towards the empirical chemistry that will develop throughout the 1700s. He also makes some studies in thermodynamics. Thermal science is not really a distinct area in his time yet, but he discovers that if you apply a quantity of heat to ice, that it's not immediately that the ice melts, that the heat remains to, as he puts it, latent in the water for a while until you build up a certain minimum quantity of energy needed to change its state. We credit him with the discovery of both latent heats and the measurement known as specific heats. Black's students carry on some of his chemical researches, and one of his students, a fellow by the name of David Rutherford, is going to isolate another kind of air in 1772, which he names phlogisticated air. Phlogisticated air is what later comes to be known as nitrogen. So we're starting to parse out that there's more than one kind of air out there, that there are distinct airs. And the guy who's really going to move this forward is going to be a rather interesting figure in that you don't see a lot of people who make a splash in both science and theology. And this guy is an Englishman, later American, by the name of Joseph Priestley. Priestley is born in 1733, dies in 1804. Becomes well known through his lifetime as a philosopher and political and social theorist, but also as a scientist. Now, Priestley is born into a dissenting family. The term dissenting churches, that's capital D in your dissenting, refers to all of the various religious movements in England, the Protestant movements that are in opposition to the Church of England. He's part of the dissenting family. He goes to a dissenting seminary. He's quite spiritual. He's ordained as a dissenting minister. But he feels that even the dissenting churches are not getting it fully right. Because Priestley believes that reason should not be incompatible with belief in God. In a time period when more and more there is an idea that science is based on reason, and religion is based on revelation and therefore inherently not rational, Priestley says, well, why shouldn't religion be rational? And he teams up with another minister of similar ideas, a fellow by the name of Theophilus Lindsay, and the two of them found a religious movement predicated on the idea of reason as a path to spiritual understanding. That movement is called Unitarianism. And there are still Unitarian churches today. There are a couple Unitarian churches in Pittsburgh. I got married in a Unitarian church. But for all of his political and social theorization, and we'll talk about political theory, Priestley is a big advocate for democratic governments. When the American and French revolutions happened, he actually speaks out in favor of them. Needless to say, that does not make him a popular man in England, and he eventually ends up fleeing to the United States, where he spends the last years of his life in the new country here. Now, Priestley, I should point out, is a fellow who is not terribly well educated in the methodology of science, and this is beginning to become a factor. Because we still have gentlemen scientists. This has not gone away. It's going to be a little while before we lose them. But Priestley has no formal education in mathematics or natural philosophy or medicine or any of those topics. Everything he knows about science is deduced from his own reading, and all of his experimental protocols are worked out basically on his own. And while it's still possible to do good science that way, it's getting harder, and it shows. If you look at Priestley's journals, they're kind of sloppy. His methodologies are poorly documented, his research notes are not the best, and it's clear that there are a lot of errors in his work that a more well-trained scientific scholar probably would not have made. Indeed, it has gotten to the point that the culture of science is growing to the point that other scholars don't necessarily take Priestley as seriously. His discoveries are important, they can't be ignored, but numerous other scientists criticize him for his lack of rigor. Now, Priestley is interested in both of the big areas of physical science development in his time, interested in both electricity and pneumatic science. In 1767, he publishes a text called History and Present State of Electricity, which summarizes most of the key electrical research that has been done throughout the 1700s. In that text, he also includes some of his own research. Among other things, he indicates the discovery that charcoal could be used to carry in electrical currents. It's going to be charcoal filaments used in Edison's first light bulb nearly 100 years later. Priestley is also the first to propose that electrical force obeys an inverse square law like gravitation, an idea that's going to be picked up by Charles Augustin de Coulomb, who was born in 1736, dies in 1806, and Coulomb is going to work out Coulomb's law, the inverse square law of electrical force. Priestley's book becomes the standard textbook on electricity for more than a century. It's going to be an inspiration to many other electrical scientists who come later, including such great names as Michael Faraday and James Clerk Maxwell, whom we'll talk about in a couple of weeks. Now, his biggest work, however, is in the realm of chemistry, and specifically in pneumatic science, the study of gases. Between 1774 and 1786, Priestley does a number of experiments with gas and ends up putting together a 6-volume work on his researches entitled Experiments and Observations of Different Kinds of Air, in which he talks about a wide range of gas experiments. Some of his works are a little bit divergent. Among other things, he discovers soda water and concludes falsely that it could be used to treat scurvy. But most of it involves the discovery of new kinds of gases. Among other things, Priestley discovers and names what he calls nitrous air, better known today as nitric oxide, acid air, better known as hydrochloric acid, alkaline air, now called ammonia, vitriolic acid air, better known as sulfur dioxide, dephlogisticated nitrous air, there's a good one. That's what we call nitrous oxide now, although Priestley did not realize what you could use it for. That'll be discovered by somebody else later. And the big one, dephlogisticated air. Dephlogisticated air is the name that Priestley gives to the gas, which now we call oxygen. And Priestley realizes that oxygen is a separate and distinct kind of air necessary for both respiration and fire. Indeed, Priestley believes that it is the best kind of air for just about anything, and he says in his text that dephlogisticated air is, quote, 5 or 6 times better than common air, I'm not sure what comes as common air here, for the purpose of respiration, inflammation, and, I believe, every other use of common atmospherical air. So, I don't think I need to tell you folks why oxygen is a crucial discovery. It's going to really make chemistry leap forward in tremendous ways, help us to understand a tremendous range of chemical reactions, help us to learn how both respiration and combustion work. The discovery of oxygen is going to advance chemistry, biology, medicine, all sorts of disciplines. It's probably the single most important chemical discovery of the century. Now, I should point out there is some dispute over who gets priority in the discovery of oxygen, because 3 different people end up claiming credit for it. Priestley discovers it, we know that. A Swedish pharmacist by the name of Carl Wilhelm Scheele, that's Scheele, discovers it as well, and based on our research notes, he seems to have been the first to isolate it. And finally, the French chemist Antoine Lavoisier, the man often regarded as the father of modern chemistry, claims discovery of oxygen, and indeed it's Lavoisier who gives it the name oxygen. It is never fully resolved which of these men is the first to get to the discovery. All of them claim priority. Priestley's research notes, being as sloppy and poorly maintained as they are part of the confusion here, because we don't know exactly when he found it. But I think it's fair to say that all 3 of them could reasonably claim credit for this very important discovery. That said, Priestley rejects a lot of the chemistry of Antoine Lavoisier. He says that it is too unnecessarily complex, and he believes chemistry should be approached more philosophically, which puts him very much out of step with the science of his day and diminishes his own scientific reputation. After he emigrates to America, Priestley is largely cut off from the scientific infrastructure of the Old World, ends up writing some papers on miscellaneous topics. Once he gets here, he writes about, of all things, the science of dreaming and about spontaneous generation of life, something that has since been disproven. He himself does not do a lot of chemistry in America, but he corresponds with Thomas Jefferson. The 2 get to be good friends and promotes the study of chemistry in America, even if he himself is not doing it. By 1801, Priestley is too sick and old to do experiments for himself, dies in 1804, and ends up sort of being kind of a forgotten figure in the history of chemistry. The French geologist Georges Cuvier eulogized him and said of Priestley that he was the father of modern chemistry who never acknowledged its daughter in his rejection of Lavoisier. So, we're talking chemistry in the 1700s. One figure who never gets a terrible amount of attention for it, because he's usually remembered for his work in physics, but he did some important chemistry as well, is going to be a rather remarkable English scientist by the name of Henry Cavendish. You might know that name. Cavendish was born in 1731, died in 1810. He was born to English nobility. His parents were English nobles living in France at the time of his birth. Cavendish was educated at Cambridge University, never finished his degree, never had to. He was a true gentleman scientist, well-educated fellow with time on his hands who didn't need to work for a living. His family's wealth supported him in comfort and style. And Cavendish lived a life of leisure as a gentleman scholar. We can all identify with Cavendish right about now because he spent the overwhelming majority of his time fearfully confined to his home. Not for the same reasons that you might be fearfully confined to your home as you're listening to this lecture, but because Cavendish was terribly, terribly socially phobic. It is believed he was probably on the autism spectrum and suffered from severe social anxiety. He hardly ever left his home. About the only time he left his home was to attend monthly meetings of the Royal Society of London, where he largely kept to himself. He actually had a back staircase installed in his house so that he could slip in and out without having to interact with his own servants. He was particularly afraid of women. At meetings of the Royal, Whenever Cavendish had something to present, he would basically scurry up to the podium, deliver it as quickly as he could, and then scurry away before anybody could ask him questions. It got to be known around the Royal that if you wanted to have a conversation with Henry Cavendish about something, what you should do is slowly approach him, but don't initiate conversation with him right away. Start talking, but what you should do is talk to the wall. Just, start talking to the wall in his general vicinity and saying some things about what you want to discuss, and let him get gradually accustomed to you and jump into the conversation when he felt comfortable with the matter. If you approached him too quickly, it was pointed out that he would hop in the air, give a little squeaking sound, and scurry away. So, private fellow might be an understatement. But in the privacy of his home, Cavendish is doing remarkable research on a wide range of topics, many of which he never becomes widely known for. Cavendish does studies on the nature of gases. He combines metals with strong acids and produces a highly flammable gas, which he calls inflammable air, a substance which Anthony Lavoisier is going to rename hydrogen. We believe other people may have isolated hydrogen in the past. I think I mentioned to you all that J.J. Becker quite possibly got hydrogen when he was trying to find phlogiston. But Cavendish is the first one to actually identify it. He goes on to do further experiments to find out the atmospheric content of our planet. What gases are present in the atmosphere in what mixtures? Cavendish finds that the approximate content of our planet's atmosphere is rather precisely here, comes in at 79.167% phlogisticated air, that is nitrogen, 20.833% dephlogisticated air, that is oxygen, and approximately 0.008%, another gas that Cavendish is not able to isolate, which we know today as argon. His numbers are a wee little bit off, but it's by a couple of decimal points. Cavendish was remarkably close in calculating the approximate mix of gases in our atmosphere today. Now, the research for which he is most famous for is the so-called Cavendish experiments, which he performed between 1797 and 1798 in an effort to determine the density of the Earth. A useful piece of information if you want to do calculations about the mass of the planet and how it's being affected by gravitational force. Cavendish sets up a very elaborate and very clever experiment in a barn on his property to work out how this might go. The way he does this is he gets himself two big old masses of lead, two 350-pound spheres of lead. And he gets two much tinier 1.61-pound spheres of lead. He suspends all of these from a torsional balance, which uses the torque on very stiff wires to measure the force of gravity acting upon those spheres. Now, he's going from Newton's premise that gravitation is a universal force, that it affects all objects equally, and he already knows to what extent the Earth's gravity is affecting these spheres. That's easily measurable. But he hangs them near one another and uses the torsional balance to measure the tiny bend in the wires as the bigger spheres attract the littler ones. And in this way, he's able to figure out, okay, what is the force acting upon those? Comparison of these forces between the balls being acted on by the Earth and the balls being acted on by one another allows him to calculate the density of the Earth using Newton's law of universal gravitation to work out the relative masses. Cavendish finds the density of the planet Earth is about 5.448 times the density of water, which is within 1% of the modern accepted value. But more importantly, his findings are of tremendous utility to astronomy and physics, not because of the density of the planet, but because they enable us to calculate the mass of the Earth, the mass of any planetary body, and by extent, to work out a vital mathematical constant that Newton did not, a number that we know today as the gravitational constant, the mathematical constant expressing the power of the force of gravity. Cavendish's experiments therefore lay the foundation for modern physics to figure out the size and mass of stars and planets by using the gravitational force with which they act on one another. You can still see that barn on his property if you go to England today. They call it the place where the Earth was weighed. It wasn't Cavendish's goal, but it ends up being what he does. Now, it is worth pointing out Cavendish did a lot of research that he never published. His social anxiety meant that he didn't always come forward with all the things he was finding. And as a consequence, poor Henry Cavendish didn't get recognized for a lot of his research. He did a lot of experiments that ended up staying in his notebooks and never seeing the light of day. Now, when he died, Cavendish, who had no family, left the majority of his fortune to a number of charities, including the endowment of a research laboratory in London. The Cavendish Laboratory is still there. Some of you might know about it. It's where Watson and Crick did their famous DNA research in the 1950s, and it remains a very prominent scientific laboratory to this day. Now, Cavendish endowed this laboratory, and he also donated his scientific equipment and his papers to the laboratory, including his unpublished papers. A lot of Cavendish's notebooks got shoved into a filing cabinet, and nobody looked at them for about 75 years after his death. Then one day, the great mathematician and electrician James Clerk Maxwell, whom we'll talk about in a couple of weeks, is poking around the laboratory, and he finds this cabinet with old Henry Cavendish's notebooks in it, and he decides to see what's in there. Maxwell discovers that Henry Cavendish, acting by the late 1700s and early 1800s, had made a remarkable bevy of discoveries that he had never published. Among other things, Cavendish had been the first, although nobody knew this, to work out Richter's law of reciprocal definite proportions, which you chemistry folks might know better as the term stoichiometry. He had also worked out Charles's law of gases, Dalton's law of partial pressure, Ohm's law, and Coulomb's law, well before any of the scientists involved had ever touched these ideas. Now, here we want to talk for just a moment about some speculative history. Cavendish had worked out fundamental principles about the behavior of electricity by the late 1700s that nobody would else discover until the mid-1800s. He was about 50 years ahead of his time in the understanding of electricity. Now, the work done in the mid-1800s by people like Ampere and Ohm would later enable us to work out Maxwell's equations. James Clerk Maxwell would work out the famous electromagnetic equations, which serve as the foundation of most of the physics that comes after, including relativity, nuclear science, and so forth. Imagine, if you will, a world in which Henry Cavendish had not been too shy to publish his work. Imagine, if you will, that we had the electrical discoveries of the mid-19th century by the beginning of the 19th century. Imagine a world in which relativity was discovered by, say, the 1830s. Imagine a world that entered the nuclear age by about the 1850s. That's the world we could have been living in. But we will not know what that world looked like because Henry Cavendish was too afraid to publish. And I'm not sure if that's a terrible tragedy for humanity or if that is a bullet that humanity dodged. All right, speaking of changing worlds, you've all taken enough history by now, some point in your life, that you know that the late 1700s and early 1800s is going to be a time of tremendous global change, not just politically, but technologically. The fruits of science are beginning to reach into society at large. The principles of physics and chemistry and mathematics that scientists have discovered are starting to reap positive, practical benefits in day-to-day life, leading to inventions and technologies that will radically change the world that we live in. Two scientists in particular bear special mention in this regard. Let us talk first off about a fellow by the name of James Watt, a Scottish engineer and chemist, born in 1736, dies in 1819. Watt's father was a shipwright. He was mostly educated at home by his mother. Became a scientific and mathematical instrument maker at the University of Glasgow. He's not there to do research himself. He's not a teacher. He's there to make tools for other scientists to use. But Watt is a practical-minded sort, good skill at engineering, good mathematical talents, and in the course of building better scientific instruments, he inevitably becomes curious about what he can make for himself. Watt does some experimentation of his own. He independently discovers the concept of latent heat, ends up becoming friends with Joseph Black. The two of them get to know each other quite well, and they actually both become friends of Benjamin Franklin, as all of them are members of the Lunar Society. Now, in 1762, Watt is poking around in the cellars of the University of Glasgow, and he discovers that the university owns an old device called a Newcomen atmospheric engine. The Newcomen atmospheric engine, named after its inventor, Thomas Newcomen, Newcomen, was built in 1712, and it was the first practical steam engine. Now, Newcomen's engine was not a very useful device. The simple fact of the matter is it was terribly inefficient. It lost most of its energy to entropic heat loss. Now, Watt, studying this thing and playing around with it, realized, hey, I'm losing most of the energy that this thing puts out to cooling. He develops the idea of attaching a separate condensing chamber to cool the engine so that not so much of its heat is lost, and therefore it can do considerably more work. By 1765, he has a good working model. He applies for a patent, gets it by 1775, but then goes through a lengthy struggle to obtain exclusive manufacturing rights to the thing, which in England was very hard to do and was separate from a patent in those days. He actually does not get his exclusive manufacturing rights for his own tool until 1794. Now, the steam engine of James Watt is about 5 times as efficient as Newcomen's, and this device will change the world. Watt's steam engine allows the production of vast quantities of mechanical energy. It allows work that was laboriously done by hand or by horse to be done by a machine, and all for the cost of chucking some coal into the hopper. Watt's invention is the beginning of the Industrial Revolution. Large-scale industry, large-scale mining operations, the building of machine-driven factories, mass production of standardized parts. Indeed, transportation technologies like the steamboats and eventually the locomotive. All of this is going to be a direct result of Watt's invention. The steam engine, quite literally, starts off industry as we know it. It becomes the driving force that provides the massive industrial power to change the entire way our economy works. And the Industrial Revolution has basically built the world that you live in right now. A world of mass production, a world of mass automation, a world in which craftsmanship that at one time required careful and laborious hand labor by well-trained craftsmen could now be done rapidly and repeatably by machines. The entire organization of the economy would change as a result of this. The steam engine is arguably the single most important technology of the 19th century, and one that is going to make an entirely different world, and the reverberations of that are still being felt now. Now, the other, by the way, you might have noticed a name in there, watts. The watt as a unit of power, appropriately enough, named after James Watt. He did not use this as the unit of power for his machine. Instead, he talked about his steam engine in terms of how the power of horses, how many horses' power could this machine do the work of, and hence the term horsepower as a unit that is still sometimes used to measure the strength of an engine. Now, the other big industrial invention that is going to radically change the world is going to be invented by an Italian physician by the name of Luigi Galvani, Galvani. Galvani is born in 1737, dies in 1797, and is often credited with the discovery of bioelectricity. Galvani was son of a physician. He himself educated in medicine at the University of Bologna and becomes the professor of anatomy there. He becomes well known for his comparative study of animal anatomy. He does a lot of experimental research with this. And he also becomes interested in electricity. He does both of these kinds of experiments in one laboratory with different benches for different kinds of research. Now, one day in 1783, Galvani has been doing electrical experimentation, but he's also got a frog dissection set up. He's got the leg of a frog hanging from a metal hook on one side of his laboratory so that he can slice into it and cut down and look at the musculature. On the other side of the lab, he has been doing electrical experiments. He has left his scalpel on the electrical workbench. Unbeknownst to Galvani, the scalpel had picked up a static charge. He picks it up, touches it to the leg of the dead frog, and is astonished when it begins to twitch and kick. After getting over the shock of being kicked by a dead frog, Galvani begins investigating what might have happened here, and he concludes that electricity was the force causing this to happen. Galvani's research leads him to the idea that electricity is a biological form of energy, the concept of what he calls animal electricity we now know as bioelectricity. Indeed, Galvani goes one step further and even says that electricity is strictly a biological phenomenon, that it's not present in other places in nature. We'll get to more about where that goes in a few minutes. Now, Galvani is going to realize on the basis of this that electricity is fundamentally the energy of life, that the motive power of living things is not some Aristotelian concept of vital heat, not some mystical energy, but rather electric currents. He shows that electric current drives muscular action, and he demonstrates that those currents are going to originate in the brain. Initially, he believes that they come strictly from muscles, but then eventually realizes that they are carried to muscles by nerves. Now, Galvani is going to end up, galvanism is named for him, chemically induced electrical current. You probably heard that term. And he's going to get into a good-natured argument, well, mostly good-natured, with another Italian scholar named Alessandro Volta about whether electricity can have animal or non-animal origins. And that is going to inspire Volta to the other great invention of the Industrial Revolution, a thing we call the battery. To finish up our story about Galvani, his discovery of animal electricity is going to inspire a whole lot of interesting research. Now that we know that electricity is the energy of life, prior to this time, even most scientists adhered to an idea called vitalism, the idea that life had its own unique kind of energy, separate from every other documented form of energy. And Galvani says, nope, it's just electricity. This leads people to begin to think, well, hey, if electricity is the motivating force of life, if I put electricity into a dead thing, can I make that dead thing be alive again? You can probably guess that this led to some fairly grisly experimentation, including experiments in which resurrection men were paid to acquire bodies. They were wired up to a battery, a voltaic pile, one of Alessandro Volta's batteries, more on that shortly, that would be set up in somebody's parlor. They would do this lovely little parlor, a resurrection party, they called them, and they'd wire up a corpse with this body set up in somebody's house, and they'd run a current through it, and the corpse would twitch away and make noises on the table as the current went through it, and everybody stands around with little flutes of champagne and cucumber sandwiches watching. Not exactly your, exciting Friday night well, I guess it's pretty exciting Friday night entertainment, but, Now, my fun little postscript here is that one person who attends one of these resurrection parties is a young English author and the original Goth by the name of Mary Shelley. Shelley, later that year, is going to be attending a writer's retreat. And the host of the retreat, because it's happening around Halloween, challenges all of the writers to tell a ghost story. Shelley, thinking back to her resurrection party, conceives the story of a mad scientist who uses electrical currents to resurrect a human corpse. And thus, from that story is born her novel, Frankenstein, the first science fiction novel. Anybody who tells you that science fiction was born from Asimov or somebody else like that, no, Mary Shelley. Absolutely. All right. I think this is a good point to take a little bit of a breather. We're partway through the 18th century. We got a bit more to go, but I've been talking to you for about an hour and a half now, and if we were in person in class, I would definitely be giving you a break at this point. So let's take a little break. I will post part 2 of this lesson in the near future. I'll see you all soon.